You feel good, right? Yoga 0% now has no artificial sweeteners and a more natural taste. You could say it makes you feel just as good. Yoga, so good. You feel good.
ഞാനേ ലൈവ് സ്ട്രീം ചെയ്യാൻ പോവാം 10 മണിക്ക്. ഉണ്ടായിരുന്നോ വിളിക്കുകയാണെങ്കിൽ കുഴപ്പമില്ല. 10 മണിക്ക് തുടങ്ങും. 2 മിനിറ്റ് കൂടെ ഉണ്ട്. എങ്ങനെ ഒന്ന് ടെസ്റ്റ് ചെയ്ത് നോക്കാൻ പോവാം. 1-2 പിള്ളേരെ വിളിച്ചിട്ടുണ്ട്. ഒരു കൊച്ചു ബാക്കി ഞാൻ തന്നെ 2-3 ഡിവൈസിൽ ഇങ്ങനെ ലോഗിൻ ചെയ്ത് വെച്ചിരിക്കുക. കാരണം എന്താ അറിയോ, ആരും ഇല്ലാന്ന് വേണ്ടത്. പണിയാണ് രാവിലെ. വിശക്കുന്നുണ്ടോ? പക്ഷെ എല്ലാം കഴിക്കാണ്ടെന്നുണ്ടോ? If you can hear me, just can you type in yes? Looks like the internet is pretty spotty. If you can hear me, just can you type in yes? Looks like the internet is pretty spotty. Okay, at least you can hear me. I'm not sure if the internet connection is pretty strong enough, so how well it will appear, it's debatable, but I'm just still going to try. I know that's we're just testing out to see whether this is a alternate way of connecting. If we have internet issues, that's what I wanted to do here today. Anyway, let me test out the PowerPoint presentation. Hopefully that will not have any lag. If it has a lag, it's going to be a problem like in the morning. Let's see what happens right now. Yeah, I do think that there is a little bit of a lag, and I can see the screens are not too sharp. One of my screens is pretty sharp, but okay, so we will get started with the simple definitions here. Molecular formula, which we are already familiar with. Any compound with the actual number of elements that are making up the molecule in the simplest ratios what we're looking at. Carbon dioxide has 1 carbon and 2 oxygen. Water has 2 hydrogens and 1 oxygen, so it's a molecule. So these are all examples of molecules. You will find that the number of molecules in number of atoms in C6H6, 6 carbons and 6 hydrogens joined together forms the molecule. So those are the examples that you have here. Now, if the compounds are ionic, we don't call them formulas. We call them molecular formulas. We call them formula units, but still, we're going to consider them as a single entity. So the examples would be sodium chloride, calcium chloride, sodium oxalate, copper 2 sulfate pentahydrate. There are certain crystals that have water of hydration with them. We call them as hydrates. So that is CuSO4 and .5H2O. That is considered as a molecule. So, and again, empirical formula. You must be familiar by now, but still, we will see how it is related. Usually, it represents the simplest ratio in which the elements are combined. We minimize the ratio in which they combine. It's not giving you the actual number of atoms, but rather the simplest ratio. So here I have the example of water. On the right side, I have the molecular formula. On the left side, again, I have the empirical formula. The simplest ratio in which water can exist is 2 hydrogens to 1 oxygen. We cannot reduce it or minimize it. So the molecular formula and the empirical formula in this case is the same. Looks like there is a lag. So the water molecule, 2 hydrogens, 1 oxygen in both the molecular formula as well as the empirical formula. Okay, let's see, take the example of benzene. Here, benzene has 6 carbon atoms and 6 hydrogen atoms. If you look at the way we can reduce the ratio of carbon to hydrogen, here we will take the highest common factor, 6. If you divide it by 6, both of the hydrogens and carbons can be reduced to 1 atom each. So if you divide the subscripts of carbon and hydrogen by 6, what you get would be the empirical formula. That would be CH. Okay, not sure if the screen is clear and sharp for you. Similarly, if you look at glucose, there are 6 carbons, 12 hydrogens, and 6 oxygens. If you divide 6, 12, and 6 by 6, you get the simplest ratio, 1 carbon, 2 hydrogens, and 1 oxygen. And that would be the empirical formula, reducing it to the simplest ratio by dividing the subscripts with the highest common factor. That's what we are looking at. Then we will get the empirical formula. There seems to be a little bit of lag, and okay, hydrogen peroxide is the next compound that we can look at. In hydrogen peroxide, there are 2 hydrogens and 2 oxygens. So the number is divisible by 2. The highest number that we can divide both of those numbers are by 2. Therefore, that will give you the simplest ratio of 1 hydrogen to 1 oxygen. That would be the empirical formula. Carbon dioxide, you can try to reduce it. You have carbon has a subscript of 1 and oxygen has a subscript of 2. And the only number it's divisible is by 1. Therefore, the molecular formula and the empirical formula are the same in this case. Butane, on the other hand, if you look at it, there are 4 carbons and 10 hydrogens. If you divide 4 by 2 and 10 by 2, you get the simplest ratio. That's the largest number by which we can divide it. So that would make it C2H5. So the empirical formula for this compound would be C2H5. So we take the molecular formula, look at the subscripts, divided by the highest common factor denominator, and then that should give you your empirical formula. Ethene, 2 carbons, 4 hydrogens, so divide by 2, you get CH2 would be the empirical formula for the compound. So we're going to move on from here. There is a simple relationship between empirical formula and molecular formula. That would help us in determining the actual molecular formula if you have the molar masses. The internet is spotty, sorry about it. I can see the screens are not moving. It's because of the connections. Looks like did not get better from morning. Okay, looks like it's taking a little bit of a time. Seems like the connection is really slowing down. I'm just checking the speed and it's really going down. Now, I think I can see it on the screen too. So I'm sure. The numbers are right on the speed test, but it doesn't seem to be reflected in the screens that we see here. So here the relationship between molecular formula and empirical formula, you divide the two, the molar mass by the empirical formula mass. Okay, thank you very much, because it looks like the rate at which it is refreshing for me, it's not too fast. So that's why I just wanted to make sure. So we're just looking at making a quick relationship between empirical formula and molecular formula. We can see that we can obtain a number that is a common factor that we'll take out of the molar masses. We determine the molar mass of glucose, we'll find it's about 180.18. We have done it many times, so that should be indicative of it. So N would be 180 by 60 by 30 would give us 6, which is the same as the highest common denominator that we use to find out the empirical formula. That number can also be obtained as the ratio of molar mass and empirical formula mass. That's what you see here, okay? I'm just waiting for the screen to refresh on a second computer to see whether it's moving forward. It's a little bit slow here. Okay. So we're going to look at the problem that you had in mind, the question that we wanted to solve. That is problem number 2, which said that the compound Y contains 69.6 grams carbon, 6.86 grams hydrogen, and remaining is oxygen. That's the problem that we're going to solve. Okay, so let's wait for the screen to come up with a problem. Some of you may be able to see it. So the problem was problem number 2 on the sheet that was given today. It said compound Y contains 69.6 grams carbon, 6.86 grams of hydrogen, and the remaining is oxygen. Determine the empirical formula of the compound. That is what we are planning to do. So in order to solve that, we will make a table. That's the first thing that we will do. We're going to make a table and put these numbers in it, and then we will see how we can, in a simple, straightforward way, solve it. So the three elements in the problem are carbon, hydrogen, and oxygen. Okay, the three elements in the compound are carbon, hydrogen, and oxygen. So we are given the percentages of carbon, hydrogen, and oxygen: 69.6%, 6.86%, and we need the percentage of oxygen. So if the third element is oxygen, if you add up the first two elements and subtract it from the 100, you should get the percentage of oxygen. So 69.6 plus 6.86, if you add it up and subtract it from 100, the percentage of oxygen is 23.54. Now you can also add up the percentages of carbon, hydrogen, and oxygen. If you're getting 99.9% or 100.1, it would be considered correct. So we have the percentages here for carbon, hydrogen, and oxygen. The next thing that we will do is we are going to make an assumption that if we are taking percentages, we also have 100 grams of the compound. Because we're talking about percentages, the 100 grams of the compound means we have 69 grams of carbon, 6.86 grams of hydrogen, and 23.54 grams of oxygen. What we will do with these numbers, we will convert them to moles using the conversion factor. For carbon, the molar mass is 12.01, so we will multiply it 69.6 using dimensional analysis by 1 mole in the numerator. In the denominator, you have 12.01 grams. The units grams and grams will cancel out, and you will have the moles of carbon. Similarly, you will find out the moles of hydrogen and the moles of oxygen by dividing it by the relative atomic masses. So which will give us the actual number of moles that we have in 100 grams. So if you take 100 grams of this compound, it will contain 5.8 moles of carbon, 6.72 moles of hydrogen, and 1.47 moles of oxygen. That's what we will have. Okay, so let's wait for the screen to refresh for a minute. My connection is spotty, that's what. Okay, it looks like the connection is still getting worse, not getting better. Sometimes it goes up, certain times it comes down. So the upload speed is a little bit slow here. That's what's really happening. So now you can see the moles, and the moles of carbon, hydrogen, and oxygen are going to be 5.80, 6.72, and 1.47 from the calculation that we have done. And then the next step is we want to find out what is the simplest ratio in which the different elements are combined. In order to do that, we will pick the smallest mole quantity. In this case, 5.80, 6.72, and 1.47. We find that 1.47 is the smallest number. So what we do is we divide all three moles by the smallest number, which is 1.47. And then we get a whole number, or we round it off to the next whole number if it is closer to a whole number. If it is closer to 0.5, we will keep it as such. So here we are going to divide 5.80 by 1.47, 6.72 divided by 1.47, and 1.47 divided by 1.47. Those are the three numbers or ratios that we're going to get. And when you do that, you will get three numbers. The numbers are 4 for carbon. You will get 4.5 for hydrogen and 1 for oxygen. These are the three numbers that we will get. Okay, so we get 4, 4.5, and 1, the three numbers that we get. And since when you write the formula of a compound, empirical or molecular, we cannot have fractions. So what I've done is, when you calculated the simplest ratio, I rounded off the numbers to the whole number. If it was closer to, if it was 3.9, I made it 4. If it was 4.1, I still made it 4. In the case of hydrogen, I rounded it off to 4.5. That's what I did. Okay, so we have 4.5. We cannot have a fraction. So when you have such a situation as you see here, what we normally do is we multiply all of it by 2 so that it becomes a whole number. So let's look at what the values are going to look like. So when you multiply it by 2, it becomes 8. Carbon becomes 8. The simplest ratio would be 8. For hydrogen, it would be 9. And for oxygen, it would be 2. That's what it would be. Okay, so we have 4 times 2 is equals to 8, and 4.5, because hydrogen was 4.5. That's the reason why we are multiplying it by 2, to make it 9, a whole number. And oxygen becomes 1 times 2 is equals to 2. So these are the numbers that we have from the simplest ratio obtained by dividing the moles by the smallest numerical value for the mole value. So that was for oxygen. Okay. Now these numbers that we get in the simplest ratio will become the subscript for the three elements. For carbon, it's going to be 8. For hydrogen, it's going to be 9. And for oxygen, it's going to be 2. Okay, that's what it is here. And therefore, we can write the empirical formula based on these numbers. So you may have got a fractional value for hydrogen. That is why you would have got a doubt over there. So for that reason, we will change that fraction to a whole number if ever the mole ratio gives us a fractional value. So in this case, we rounded it off to the 0.5 range, but if it was 4.9, I would have rounded it off to 5. Okay, but it was closer to 0.5, therefore I rounded it off to 4.5. And now we multiplied it by 2 so that we get whole numbers for all of them. So using this, we can actually write the empirical formula of the compound. So here, C8H9O2 would be the empirical formula, because we have the simplest ratio tells us it's C8H9 and O2. So that would be the empirical formula of the compound. Okay. So here is the empirical formula for the compound. And let's okay, it's mostly it's my screen over here which is giving this problem. Hopefully you can see the final screen. I have one more problem which you had the doubt on. So I'm going to solve that one. Okay, so let's move on to the next slide. So your final answer for the question number 2 would be, the empirical formula would be C8H9O2. And the reason was, for hydrogen we had 4.1, 4.5 as the mole ratio for the simplest ratio. Okay, so that's the first problem, the problem number 2, which you had a question with. Next let's look at problem number 3. Here we have a sample of a substance is determined to be composed of 0.8089 grams of potassium, 1.18 grams of chromium, and 1.27 grams of oxygen. So we have 3 elements, and the ratio is going to be 0.89. I mean, not ratio, the masses of these compounds are 0.89, 1.18, and 1.27. Now here, instead of giving you the percentages, we actually gave you the grams. In the previous case, we used the percentages and then we converted it into moles using making the assumption if we had 100 grams, what would be the value. So here you don't have to do that. You can determine the moles directly because you are given the grams. The mass is given to you. Okay. So that's the part that is different in this problem from the previous problem. In the previous problem, we started with the percentage and then we changed it into grams and then we solved for the moles. That's what we did. In this problem, you're not given the percentage, you're given the actual weights of the elements in a compound. So you can use these masses to find out the moles. That's what we will be doing here. Okay. So the 3 elements that you have here, so the 3 elements that we have here are potassium, chromium, and oxygen. So here we have given you the grams of these 3 compounds. So the next step would be to convert it into moles. So we convert it into moles, grams to moles, we already know. We can take the mass and multiply it by the conversion unit. For every mole, you have the molar mass is the mass. So in the case of potassium, it is 39.10. So 0.89 grams into 1 mole by 39.10 gives you the moles of potassium. Similarly, we get the moles of chromium, 1.18 times 1 mole by 52. And the moles of oxygen would be 1.27 into 1 mole divided by 60, the conversion unit. So we have 3 different percentages here. I mean, 3 different moles here. We calculated the moles of potassium, chromium, and oxygen. These parts are pretty clear. The only difference in this problem is the masses of potassium, chromium, and oxygen are given. So it is easy to calculate right away the number of moles. The value for the moles are 0.0227 moles of potassium, 0.0226 moles of chromium, and 0.0793 moles of oxygen. These are the 3 quantities that we have. So once we have those 3 quantities, then you can find out the simplest ratio in which they react. So we're going to divide all of these 3 numbers by the smallest number. So the smallest number is 0.0226. Okay, so we're going to take that number and divide the moles of potassium, chromium, and oxygen using that. So if you divide it, 0.0227 by 0.0226, all the 3, when you divide it by 0.0226, you will get three different numbers. The values are going to be 1, 1, and 3.5 in this case. So we have three values here. It's 1, 1, and 3.5. Okay, so once you have that value, then you find that 3.5 is not a number that you can actually make it part of an equation or a formula. We cannot have fractional values. So for that reason, like in the previous case, if you multiply all of these three numbers by 2, then the 3.5 goes away and you get a 7. Then potassium and chromium becomes 2 each. So that gives us the empirical formula for the compound. That's what's going to happen. Okay, so we're going to multiply that by 2. When you multiply that by 2, it's going to change into 2, 2, and 7. So the empirical formula will change into K2Cr2O7. That would be your final answer. Looks like my internet is not working at all. The upload speeds are really, really slow. Something's happening. I did try to call them up and they said they fixed it, but it's not fixed. That's what I see right now. Probably it's a marketing ploy to get me to change my plan. Anyway, so if you look at the final screen, probably it'll come up. Potassium, when you multiply it by 2, the final answer would be 2. Chromium would be 2, and oxygen would be 7. Okay, so you can have the empirical formula of the compound. It will be K2Cr2O7, and that's how you obtain the final answer. So hopefully this has cleared your doubts in terms of solving problems using for molecular formula and empirical formula. Here these problems were chosen because while you determine the mole ratio, you will get a fraction, and that sometimes leads to a little bit of a confusion. So that was the reason why these two problems were chosen, and hope this has cleared the doubt and you can explain the answer that you got and correct it to this final answer that is based on changing the fractional values to the whole number. Okay. So that's it for now. I don't want to still hang on here. It looks like my connection is not going to improve, and tomorrow is going to be a problem again. I have to see what I can do alternatively. So in the meantime, hopefully this question has been answered. If you still have any doubts on it, you can type in the chat and I can try to respond verbally.